Okay guys, in this video we're gonna start now chapter 3. Chapter 3, and in your textbook this chapter is title is energy. Okay, so the first thing I want to start is again I'm trying to explain you guys some concepts here, and when you try to solve problems, usually the problems in this textbook is plug-in problems, but I still like to go into the concepts and like to describe the concepts in details so that you can actually understand the process when you solve problems. Now, so we start with chapter 3. We're going to start with explanation of energy, and I'm going to explain what work is. And the way I'm going to do it is, let's say I have some object and it travels with a certain velocity, and let's say it's a constant velocity. There's a constant velocity. All right. So here during this object displacement, you got acceleration which is equal to 0, and the net force is also equal to 0, of course. Now, what happens now if your acceleration or your velocity now starts increasing? You got now a little bigger velocity here, then here, and then here. And so eventually you're gonna realize here that from here to here, what's happening now is that you got some acceleration constant. You have some constant acceleration, or of course you got F net will be now not a 0, but equal to m times a. Now, what does it mean? It means that here you had a state of inertia, or this object were just in equilibrium, and there was no external force to change this object's velocity and acceleration. Now, in this particular moment, now we got the second law of Newton. This is where you disturb now this was inertia here, but now you disturb the equilibrium here, and the external force applied, and so F net now will change the, of course, the velocity, and I just showed it, guys, by the different magnitude of the increasing magnitude of this vector velocity. And let me just put it here: v1, v2, some v3, v4, v5, v6. And so now you got you disturb now from the equilibrium here this initial part of the displacement, but here now you got the force applied. And so this force now, we can also express acceleration as a equal to F o divided by m. And we learned before a couple of different concepts about displacement velocity, so I'm going to state the formulas here, and then when we put everything together, you will see now something interesting here that we will develop. So we learned before the following formulas. We learned the d final, or final displacement, is equal to d initial plus vi tf plus 1/2 at, and this is of course vector here, tf t final squared. Now, I derived this formula during our face-to-face meetings, so you should go to your notes, should go back to your notes and just check the formula. Now, the other formula that we also did derive was v sub f is equal to vi plus a t sub f. Now, and from this formula you can find that the t sub f is equal to v final minus v initial divided by a. And so I'm going to give you now the third formula, which you can derive now based on these two formulas. Now, again, use some algebra, you substitute. Now, let me just state the formula. So you take now this t final and you substitute it for this t final here and for this t final here. So eventually, when you do a series of rearrangements here, you're going to get this formula. TAD is equal to VF squared minus V initial squared. And now this formula is kind of important here. And I know I did not show you guys this formula during our face-to-face meetings because it's just, a lot of rearrangement here needs to be done in order to make out of these two formulas this formula. And again, if you have a question how to do it, you can always email me and I send you guys a solution for it. So now, what is this? Why is this formula important? Well, let's get to it. So we know that the acceleration here is F over m. So I can substitute now, instead of this a, I'm going to put F over m. So it's going to be 2F over m times d is equal to Vf squared minus Vi squared. And so now we can just find out F times d will be now equal to 1 over mv final squared minus 1 over mv initial squared. We're almost there. Now, so this force here is pretty much applied in the direction of the displacement, as I showed here. So I'm going to put just this little vector here, a little vector here. So now the force is moving this way, because remember how we found before the delta V here? We took V final, V6 minus V initial. So we took this vector, we took this one, add them by flipping this one, and then you will see that the resulting vector will be pointing in this direction, okay? So therefore, the force is also pointing to this direction. And remember, we have a displacement from here to here, so it's in the same direction displacement, okay? So that's kind of important with the signs later on. You will see it, guys. So now, so we got force times distance is equal to, there's a smudge in here, V square final minus 1/2 mv initial square. And so what is it giving us here now? So the work, guys, the work is defined, and you can see in your book, is the force times distance. Okay, so it's a product of force and distance and displacement now. And what's so interesting here now, I got this formula here. So how do they relate here? It's a good question here, right? Now, and the way they relate, first I have to answer the question, what is the 1/2 mv squared? Where is it? And it is pretty much the object's property here. So if you have some car that is moving with a certain velocity here, and so what this car can do, guys, when it has an impact with some other car or with something else, it will be able to change either itself or things surrounding it, or the environment, okay? So this is nothing else. What this describes what's called some kind of energy. So again, the energy is the, in this particular case, this formula describes some kind of motion. So the energy here associated with some kind of motion, and the energy is nothing else is when that motion in this case can change itself or the surrounding or environment around itself. So that would be energy. But what kind of energy is this one? This energy here associated with the motion. And so this energy we called kinetic energy. 1/2 mv squared. Now, so if you now take a look at this equation here, we substitute F times d as W, and this W will be nothing else is 1/2 mv squared final minus 1/2 mv squared initial. And so we know now this is E sub k, kinetic energy, E kinetic energy final minus E kinetic energy initial. So work as the object moves is nothing else as the change in kinetic energy. Okay, and that's important because work is not a type of energy. Work is just transfer of energy. And again, as my previous example with the car, car is moving, it has some kind of energy right now, energy associated with the motion. But when it creates an impact, what it does with something, it moves something certain distance, it creates a transfer of energy. And so the work is not a type of energy, it's a transfer of energy. It brings energy, for example, from a certain object to the rest of the universe, I guess, or to the surroundings, or to the environment. Okay, and so this is a kinetic energy. Now, so the work as the object is moving and accelerates is nothing else as a change in kinetic energy. Now, kinetic energy, or energy, guys, we use the units of joules. So what is a joule? And a joule could be explained in terms of kinetic energy here, is when you have a 2 kilogram object, like let's say a book, that it moves with a velocity of 1 meter per second, you get equivalent to 1 joule here. So what are the units of joules? How you can break it down into the simpler units? It is, from this, you can see it's kilogram times meter square divided by the second square. And that's what the joule is, guys. In the next video, guys, I'm going to talk, maybe solve some problems. I'm going to talk about different types of energies. Now, the question could be, is that the only way the work could be done through the motion of an object? And the answer is no, because it can also have stored energy, and the stored energy can also do some work. But again, that will be covered now in the next video.